For derivatives of trig functions, we will start with sine. So here's our sine curve from 0 to 2 pi and 0 to negative 2 pi. And we have a tangent line drawn at 0. Can you see the slope of that tangent line is 1? What's the slope going to be at pi over 2? 0. 3 pi over 2 is going to be 0 as well. Can you see that the tangent would be flat at those places? At pi, looks like it's going to be a negative slope. So if we drag this along, okay, sure enough, there it's 0.
Hello?
Hello?
Hi, sorry for interrupting. Is that an okay time for Musa to come to the office?
Right, we will continue dragging this along. Goes down here at 0 again. I like how it pops at those places. Pop. Oh, it didn't pop at that one, of course. So we draw it along. And like, oh, that sure looks like a graph that I know what that is. What is our derivative graph? It's cos. And so we have, which is really, it's really cool if you think of all those slopes, graphing them all, putting them together, perfectly fits with cos. So we go to our notes here, we can say the derivative of sine is cos. Now you're going to have these memorized. And so one of the things that I find helpful for remembering that the derivative of sine is cos, because they're going to be all so similar that they're going to be easy to mix up. Trust me. Okay? So I always think back of this to this graph. Think back to this graph and think back to this tangent right here at 0. It's pretty easy to imagine that tangent line at 0. And it's pretty easy to see that that tangent line has a positive slope. And so having that starting point up here and then drawing a sinusoidal is going to draw cos. Some of the things you can see about this, it's going to be a positive slope up to here, and then here it's going to be 0. Negative slopes here. Notice this is quadrant 2 and 3 that the slopes are negative. What function is negative in quadrant 2 and 3? Cosine. So if you imagine the graph in your head and you imagine drawing a couple of tangent lines to it, you're going to remember that the derivative of sine is cos. Okay? Just by the fact that starting right here at 0, it has a slope of 1. What function starts, what sinusoidal starts at 1? It's going to be cos. Because when we get to our cos graph, which we're going to look at right now, next, I'll make that bigger. Can you see that your cos graph is going to start at a derivative of 0? And if you drag it to the right, will the tangent line have a positive or negative slope? Negative slope. So as we draw it to the right, notice that our slopes are in the negative already. Right? They're going to be negative all the way until we get down to here where it's 0 again. And then these are positive. And so if we drag this along, oh, it looks like another sine or cos graph. What's the best way to describe this equation? There we go. Here, draw it in. Oh. Yes, there we go. Perfectly filled in. The equation of that graph is negative sine. Okay? So the derivative of sine is cos. The derivative of cos is negative sine. Later we have to work backwards. So working backwards from cos is positive sine, and working backwards from sine is negative cos. So the negatives and the positives get mixed up depending on which way you're going. And so it becomes hard to remember, just because they're so similar. Which one does the negative go with? If you're just trying to memorize it, You will make those mistakes sometimes. You'll get them mixed up. But if you can think back to the graphs, if you can think back to your cos graph and say, I know that it's flat here at 0, and if I move to my right, my tangents are going to have a negative slope. That's going to help you remember that the derivative of cos is negative sine. And if you think of your sine graph, positive slope to start with, so it starts at 1, that's going to match up with your cos graph. Okay. And finally, we're going to look at our tangent graph. Again, I'll make this a little bit bigger. Right, it starts at 1. Look at your tangent graph and think about putting tangents on tangent graphs. What are the slopes of your tangents going to always be? They're always positive. Can you see that? No matter where I draw this, my slope is positive there, positive there. I go on to this one, positive, positive. Right, this is so much fun. All right. Hopefully you can see what it looks like, even though not all the dots. Oh, I want a few more in this one. There we go. There. This graph might be a little bit more difficult to figure out what it is. It looks like a bunch of parabolas, doesn't it? Okay. What other graphs does it look like, kind of? Okay. A secant graph would have it at the bottom too, right? Kind of like half of a secant graph. Maybe the absolute value of a secant graph. That might make sense. Okay. That's close. What also would make, like absolute value would make something positive. What also would make something positive? Squaring it would make something positive. So this graph ends up being a secant squared graph, or 1 over cos squared. Do you remember your trig identity? Tan squared plus 1 equals secant squared? Okay. This, making connections like that, they really don't have much in common. They're not actually the reason why the derivative is secant squared, but the fact that you've got an identity that relates tan to secant, that helps me remember that the derivative of tan is secant squared. It's just a connection of tan is related to secant squared in our identities, and in our derivatives, the derivative of tan is secant squared. Derivative of cotangent, secant, and cosecant, just making sure I remember which one. They're a little bit different. Cotangent becomes negative cosecant squared. Cosecant is cotangent times cosecant. They're weird. One of them is positive, one of them negative. I always derive them by using the rules that we're going to learn next. But first, now that we've got our rules for sine, cos, and tangent, now we can find the derivative of new functions like this, with numbers in front, adding some of the things that we've learned before, like our power rule, and so on. And so having a number out in front doesn't matter. What's the derivative of sine? Cos. So the derivative of 4 sine will be 4 cos. Here we have 3 things separate. We can do the derivative of each of them separately. What's the derivative of cos? Negative sine. What's the derivative of tan? Secant squared. And then the last one we can do already. So putting a negative sign in there would make that positive 1/3 sine. Then tan would be secant squared. And finally, the power rule that we know already. The 3 comes out in front. Subtract 1 from the exponent. Yeah? Do we have to graph what? Graph this whole thing right now? No. We will be graphing a bunch of things. We're going to learn how calculus can extend your skills at graphing from grade 12, but that's our next unit. Were you feeling, I mean, we're into unit 3 and we haven't done any graphing. Are you having like a graphing void feeling? Because in grade 12 we graph so much that it's like every other unit was a graphing unit. Are you feeling like, oh, I'm really missing graphing? No. Okay. Well, that's good. We do have, next unit has a graphing component, but that only part of the unit, and that's our only graphing part of this year. Oh, everybody loves graphing. Okay. Currently, this function is not in a form that we can do the derivative. We have learnt no rules yet for putting numbers inside of sine. We can do the derivative of sine, but you are not allowed to do the derivative of sine 2 theta. Plus, we're dividing right now. So currently, this is not in a form that we know how to do the derivative of. Okay, we're going to add rules so we can do derivatives in new forms, but currently, this isn't in a form that we can do. So either A, we have to change it into a form we can do, or B, give up. Okay. Unfortunately, I think you guys have used the give up strategy too much in the last week, so it's no longer available. What could you do? What could you change? We know an identity for sine 2 theta. You could change it to 2 sine theta cos theta. How would that help? Oh, your signs would go away. And then we are just have the function 2 cos theta. What? No. So this is a good question. 2 sine theta divided by sine theta. The question is this just sine theta? No, the answer to this is 2. If you have sine squared theta over sine theta, this would be sine theta. Right? And if you think about numbers, if I have 2 times 3 divided by 3, is this 3? No, this is 2. They simplify, the 2 stays. So sometimes if you're unsure of something algebraically, because you're dealing with functions, think back to numbers, think back to the rules you would have with regular numbers, and you can see why it works. So then we have just 2 cos theta. So the derivative of 2 cos theta, what's the derivative of cos? Negative sine, so this becomes negative sine 2 sine theta. And so then we have our tangent questions as well. Let's find the equation of the tangent and the normal, just to practice, to y equals sine of x at the origin. So how do we find an equation of tangent? We're going to need a point and a slope. We already have the point, 0, 0, at the origin. And our derivative of sine is just cos. So if we plug in 0 into cos, we find the gradient or slope of our tangent. Try to use the word gradient as much as possible because you're not used to it like you are used to slope. So you get familiarized with it. So the gradient will be 1. So now that we know our point and our slope, we can find our tangent. and our tangent line just becomes y equals x. If we were figuring out our normal, our slope would be the negative reciprocal, which is -1, and so the equation of the normal would be y equals -x. Here's a picture of what's happening. The red line we already saw when we looked at our GeoGebra app. We could see that that slope tangent line would be right there, and there we have the normal line that goes with it.